Bien, donc bienvenue pour ce séminaire du laboratoire Jacques-Louis en formule hybride. La situation est très évolutive, donc on enverra un message. On enverra un message pour dire comment vont se passer les séminaires prochains, si on revient à une formule purement distancielle, si on reste en hybride, mais avec quelles contraintes de contenance pour la salle. Et donc aujourd'hui, on a le grand plaisir d'accueillir Katharina Schratz, qui depuis maintenant une petite année est chez nous à Sorbonne Université. Et elle va nous parler de l'utilisation des résonances comme un outil de calcul. Katharina, c'est à toi.
Merci, merci beaucoup. Et malheureusement, je dois commencer mon exposé avec une apologie parce que je vais parler en anglais, mais j'espère que bientôt je peux aussi donner des exposés en français, bien sûr. So I will talk about resonances, resonances as a computational tool, and this is a recent novel integration technique I was working on in the last couple of years, and this is also the main subject of my ERC starting grant. So what is the motivation behind this? Basically, what we understand in numerical analysis already quite well are smooth solutions. So for instance, if we look at the solution of the nonlinear Schrödinger equation for some smooth initial value, the solution stays smooth and we can easily approximate it numerically. This, however, drastically changes if we take a non-smooth initial value, such as a step function. The solution is no longer smooth and the numerical approximation fails. And this is still one of the big challenges in computational mathematics, non-smooth phenomena arising in nonlinear PDEs. And in particular, a big problem this is in the context of dispersive equations, because for instance, in contrast to the parabolic setting, we cannot expect any smoothing. So if we start rough, basically we stay rough. Nevertheless, there are a lot of very interesting phenomena arising for dispersive PDEs at low regularity, for instance, blow-up solutions, high-frequency regimes, or quantization effects. And this got me interested in the question in how far we can approximate the dynamics of dispersive equations also under low regularity. And the importance of this question, you see, when, for instance, you think about the numerical simulation of blow-up phenomena. In the end, what you see on your screen is a blow-up. But you have to make sure that your numerical scheme is reliable and that you track actually blow up in a continuous problem, so the real blow up, and that you do not only see a numerical instability. And so this got me interested in this subject, and in the last years I was developing a new integration technique which with the main aim to allow approximations also in a more general setting, namely under low regularity for these dispersive equations. And to illustrate the underlying idea of this novel integration technique, let us look at one particular problem, namely the Kdv de Vries equation. So the Kdv equation models shallow water waves, and mathematically it is described as an evolution equation, where the time evolution of the solution is driven by a third order differential operator dx cubed, and then we have a Burger's nonlinearity. Now, before I present the main idea behind my new integration technique, let me first give a brief overview on classical numerical methods to solve this Kdv equation. Because in order to obtain the idea for the new integration method, we first have to ask ourselves, why do classical methods actually fail? And so one of the most famous methods to approximate the dynamics of the Kdv equation are splitting methods. So the basic idea of splitting methods is that you have a complicated problem, you take this problem and you split it into a series of simpler subproblems. Then you solve the simpler subproblems and compose their flows to get an approximation to the original solution. So numerically speaking, we face two main difficulties in the Kdv equation. We have the third order differential operator, and we have the nonlinear term, the nonlinear term dxu squared. And so the basic idea of the splitting method is now the following. Instead of approximating the full equation, in the first step, we only take the linear part. So we forget about the nonlinearity in our equation, and we just consider the linear part in the equation. And then in the next step, we forget about the linear part in our equation, and we simply look at the nonlinear equation, which is the Burger's equation. Now, numerically, we can solve these two sub-problems in a much more efficient way. For instance, if you think about spectral methods, we can solve this linear equation exactly in time. And if we stay on the time discrete level, also we can solve this nonlinear problem exactly with, for instance, the method of characteristics. But now, of course, we do not want to have an approximation to the sub-problems. In the end, we want to have an approximation to the full solution. And now this is where the splitting idea comes into play. Namely, the idea is the following. If we start here with our initial value u0, and then let us assume that our exact flow with time step tau would take the initial value and transport this up here. So this would be the exact solution at time tau. And now the idea is, instead of following the exact flow, we make one step into the direction of the linear flow. So here we simply solve the subproblem S1. Then we end up somewhere here. And then we take this as an initial value and we make one step into the direction of the nonlinear flow. So here we solve the second subproblem. And this then we take as our numerical approximation. So this is a first order approximation. Of course, we can also think about higher order splitting approaches. For instance, if we look at the symmetrized version of the splitting, where we make half a step linear, full step nonlinear, half a step linear. This is the so-called strength splitting method, which is of second order. In the end, what we're interested in numerical analysis is, of course, the approximation error we are making. So in the end, we want to know how close our numerical approximation is indeed to the exact solution. And so in the last years, Holden, Lubich, Resebo, Carlson, and Terence Tao could for the first time establish a global error estimate for the splitting method applied to the Kdv equation. So what they could show was the following, namely, if you measure the error, so the difference between the exact solution and the numerical solution at some time tn in the Sobolev norm H1, then you get second order convergence in time if two assumptions are satisfied. Namely, first of all, you assume that the Burger's equation is solved exactly. And this is, of course, true on the time discrete level, because you can just say you use the method of characteristics. But in the end, we have a PDE, so we also have to apply a discretization in space. And here you have to be a bit careful, because if you solve the Burger's equation, on the one hand, shocks can appear if you take two large time steps. And secondly, of course, with the method of characteristics, you do not necessarily end up on the discrete points in space again. Okay, this is one assumption for the convergence result. And the second assumption is that you need a lot of smoothness in the solution. Namely, basically what you need is that your solution lives in the Sobolev space H6. Now let us look at the second classical method to approximate solutions of the Kdv equations. And these are the so-called exponential integrator methods. So the basic idea behind exponential integrator methods is that you do not discretize the equation directly itself, but you look to the mild solution. So the mild solution of the Kdv equation is given by Duhamel's formula. And basically we can express the solution at time t by the free Kdv flow exponential minus t dx cubed acting on the initial value. And then we have basically the integral over this free Kdv flow acting on our nonlinearity at time s. Now, if we want to make use of this Duhamel's formula in numerical analysis, of course, we somehow have to discretize this integral. And the basic idea of the exponential integrator method is now to say, okay, if my time is not too large, then my nonlinearity will not change so much between 0 and t. And so the simple idea is just to freeze the nonlinearity at the initial point 0. Okay, because of this, you can just do by a simple Taylor series expansion. And then what you win is, if you do this Taylor series expansion, so you freeze your nonlinearity, then of course you can pull it out of the integral. And what you're left with, because it does no longer depend on the integration variable, and what you're left with is the integral over the free Kdv flow. But this, of course, you can solve exactly. And this then already gives rise to the first order exponential integrator method. So what you do is you forget about this error you introduced by the freezing process, so just this Taylor series expansion error, and you take these two terms, which are now discrete in time, as your numerical approximation. Okay, and this is the first order exponential integrator method. So how does it look like? Let us take a closer look. I take my nonlinearity frozen at the initial value, and I transport this nonlinearity with the integral over the free Kdv flow, which is the so-called phi1 function. And then I simply add up this term, which I have as the first term in my Duhamel's formula. Okay, and so for this exponential integrator, what we can easily see is what local error we introduce, because this is just this Taylor series expansion error we produce by approximating our nonlinearity at time 0. And so what we see is in the local error, we make a Taylor series expansion in time of the solution. So we introduce this error of dtu, and then we have an additional dx term because we have the Burger's nonlinearity. And then if we want to know how much regularity we need in order to bound this local error, we just have to look into our equation. So we have to say, what is the worst term, so to say, for dtu? And then we see in terms of the derivatives, we see that dtu behaves like basically like dx cubed. Okay, so the local error, we see we need smoothness, we need at least the boundedness of 4 additional derivatives. But what is surprising for the global error analysis, because of course we do not only want to use this as a one-step method to start with the initial value and make one step, but in the end we want to solve the PDE on 0 to capital T, and so we have to iterate our numerical scheme, and in the end we want to establish a global error estimate. And interestingly, for this exponential integrator method, for the Kdv equation, even if you would assume the infinity solution, no global error estimates could be established so far. And this somehow got me thinking, because the Kdv equation is such a fundamental model problem, but if you look at these classical methods, it's very difficult to show convergence of them, and in particular, they need a lot of smoothness in the solution in order to allow approximation. And of course, in the next step, the question was, can we develop new numerical methods which allow to approximate solutions of the Kdv equation also under lower regularity assumptions? And in order to answer this question, we first have to understand on a deeper level what actually the problem of these classical methods is. And if we want to understand on a deeper level what the problem of the classical methods is, we have to understand the underlying structure of the Kdv solution. If we want to understand the underlying structure of the Kdv solution, we again turn to Duhamel's formula. So we write down Duhamel's formula. So again, at time t, I can express my solution as the free Kdv flow acting on initial value, and then I have the integral over the Kdv flow acting on the nonlinearity. And now, if I want to get a rough idea of the structure of the solution, what I do, I just iterate this formula. So basically what I can say, so I want to have an approximation of this nonlinearity. I want to have a feeling how this behaves. And so basically, if now I set t equal to s in the formula, I see that u of s behaves in the first approximation as exponential minus s dx cubed acting on the initial value. And then we have some higher order terms involving the integral from 0 to s. And now if we want to get a rough idea of the structure of the solution, what do? We forget the higher order terms, and we simply plug the first iteration of Duhamel's formula into our nonlinearity. And then what we see is the following, namely that the underlying structure of the Kdv solution is driven by the nonlinear frequency interaction of the operator exponential s dx cubed and exponential minus s dx cubed. And so if we want to understand in how far our numerical schemes stay close to the actual structure of the solution, we have to understand and we have to see in how far our numerical scheme resolves these nonlinear frequency interactions. And this is where you easily see the problem behind these classical methods, because they mostly stem from linear ODE theory. And this is why they approximate these nonlinear frequency interactions in the system only in a linear way. Okay, so for instance, if we look at the splitting method from a frequency point of view, it approximates these nonlinear frequency interactions as if you would have a linear problem. Because of course, if f would be linear, these frequencies would indeed cancel out. But in general, for the nonlinear problem, this is not the case. And on the other hand, exponential integrators, they simply swallow all the frequencies within the nonlinearity. And this is somehow the problem with these classical methods, because they completely decouple the interaction of the differential operator and your nonlinearity. And this is also what you see, where let us go back to the method. So for instance, if we look at the splitting method, what you do is you take your nonlinear PDE and you split it into the linear part and the nonlinear part. And now, for instance, if you would change your nonlinearity, so not look at u squared, but u to the power of 2p, you would not change at all how you solve the linear equation. Okay, so when you solve the linear part, it doesn't see what nonlinearity you actually have. And this is similar for an exponential integrator method, because basically you take your nonlinearity and you just transport it with this the integral over the free Kdv flow. But again, this phi1 function does not really take into account the structure of the nonlinearity. Okay, and this is somehow the problem of classical methods, because this linearization of frequency interactions requires a lot of smoothness. And this fact you also see in numerical experiments. So what we see here is a numerical experiment where we solve the cubic Schrödinger equation with H1 data. And what we see is a convergence plot of these classical schemes, the least splitting method, the exponential integrator method, and the strength splitting method. And now what we would, and so in the order plot, on the x-axis, we plot the time step size, and on the y-axis, we plot the error in double logarithmic scale. And now, classically, what we would expect, so if we would be smooth, if we would be in a smooth setting, what we would expect is that the least splitting and the exponential integrator converge with first order, because they are first order methods. And as a reference, I've plotted here in dashed a line with first order slope. Okay, so we would expect that this least splitting and exponential integrator method behave like this. And the strength splitting method should have second order, so it should be parallel to this line. And then when we look in this convergence plot, we see that this is absolutely not the case, because these methods really break down under low regularity and they do not reach the order of convergence. So we see that the exponential integrator method converges very slowly, and the error of the splitting method, they also do not reach the convergence. And in particular, the error starts to oscillate widely, and you cannot have a reliable approximation. And what you also see is that under low regularity, it does not pay off to take higher order methods, because in the error you do not see any difference between the least splitting method of first order and the second order strength splitting approximation. Okay, and now probably you already have an idea what my underlying idea was, how to develop a new integration method. Namely, the underlying idea is, if you want to allow approximations also under lower regularity, then you indeed have to take this nonlinear frequency nonlinear frequency interactions into account. So you have to go away from this linear frequency approximation, which are always the case for these classical methods. And now, if we want to talk about solving the Kdv equation, of course, we have to impose some boundary conditions. And for the moment, let us simply impose periodic boundary conditions. Okay, and this is what I call resonances as a accommodation tool, because basically the underlying structure of resonances of this PDE exactly tell us how these nonlinear frequency interactions look like. And my idea was to go away from this linearized frequency approximations and embed this nonlinear frequency interactions with the underlying resonance structure directly into the discretization. And the inspiration for this was actually from the analysis of PDEs, because basically you have the same problem if you want to show local well-posters of the KdV solution in low regularity spaces. You also have to take the particular structure of nonlinear frequency interactions and the corresponding resonance structure into account. Okay, so now the question is, how can we build a numerical scheme which actually embeds these nonlinear frequency interactions in the discretization? And the simple idea is to say, okay, let us first forget the higher order terms, because, okay, this will just be a local approximation error, for instance, of order 2. And what the central thing is really to find a good discretization of this oscillatory integral. Okay, and so I copied just the line of the oscillatory integral, and now is where these periodic boundary conditions pay off, because the periodic boundary conditions allow us to really describe these nonlinear frequency interactions. Because what can I do now if I type, so I want to discretize this oscillatory integral, and what I can do, I can take my function v of x and express it in Fourier space, okay? So I write it as the sum k and z, bk hat times exponential ikx. And now if I want to discretize this oscillatory integral, what I have to understand is how this operator, this Kdv flow, acts on my function. And so basically I can look what happens if I now apply to my function this operator exponential minus s dx cubed. And now in Fourier space, I see that this operator, of course, only acts on my Fourier basis. And I see that this operator in Fourier space is nothing else than a Fourier multiplier, which behaves like exponential plus ISK cubed. Okay, and so now I know exactly how my Kdv flow acts on the solution. If I want to know how it acts on the solution, I go to Fourier space and I see this is just a Fourier multiplier, exponential ISK cubed. Okay, and so this is basically what I do to understand the structure of this oscillatory integral. I expand my function v into Fourier series. Okay, and so I have a v square here, so I get a vk hat and a vl hat. And then as I know how these operators act on my functions and the product of these functions, I can simply collect all these Fourier modes in the so-called resonance structure R. Okay, so this is just taking your function Fourier series expansion and collecting all these nonlinear interactions together. And for the Kdv equation, for instance, we see that this is a very particular structure, namely this R, if I collect all my frequencies, I see that this is a multiplication of one frequency k with the other frequency k, and then multiplied with the sum of the two. Okay, and now what can I do? I can just plug in the structure into my integral and solve my integral exactly. Okay, this is what we have on the next. Now what we see is that we get an exact expression of this oscillatory integral in Fourier space. Okay, this is just Fourier series expansion, collecting all my nonlinear frequency interactions and then integrating the thing exactly. Now, here somehow where analysis and numerics pave the ways, because in analysis, what you have to do is you somehow have to control these resonances. But in numerics, for us, what is very important is that now, when we have this oscillatory integral in Fourier space, we want to map this back to physical space. Because in numerical analysis, we do not want to carry out our computations in Fourier space, because this would be very expensive. So here in this setting, you can say, okay, we're in one dimension, we only have a quadratic nonlinearity, so you could practically compute this in Fourier space. But if you think about higher dimensions and higher polynomials, your computation effort would just explode. Okay, so what you want to do is in numerics, you always want to multiply two functions in physical space and carry out the differentiation in Fourier space. Because then with the fast Fourier transform, you can easily change the pictures very efficiently. And so what we see is that in the situation of the Kdv flow, you can really map this oscillatory integral back to physical space. And what you see is that basically you get the nonlinear frequency interactions applied to some modified nonlinearity. Okay, and now this you already have your resonance-based first order approximation. So what you do is, again, you forget the higher order terms, you plug in what you found as your oscillatory integral, you plug in what you found as your for the oscillatory integrator, you plug this in here. Okay, so here we could do this exactly, and then you add it with the first term, and this is your numerical scheme. If you forget these second order terms here. And so here I've written down this first order resonance scheme for the Kdv equation, and together with Martina Hoffmanova, we could establish global error estimates for the scheme and show that you get global error, you get global convergence under far less regularity assumptions than with classical schemes which simply linearize the frequencies. And now if you think about the Kdv equation, it has a lot of structure. It's a completely integrable system. And so in numerics, what you want, you don't only want to show convergence, but you also want to know in how far your numerical solution preserves this particular structure. And one nice thing is here to look, for instance, at solitone simulations, because solitones, basically you start with your initial shape, and then the solitone moves to the left or to the right, depending on the sign. And now you want to know how your numerical scheme reproduces this solitone solution and whether it also preserves the shape. And so what you see in this numerical simulation, you see the solitone in yellow dotted, you see the resonance space scheme in red, and in blue you see a classical exponential integrator scheme. And so you see from time t is 0, time 21, and time 24. So the exact solitone just moves to the right, and then we look a little bit closer how our numerical methods behave. And so I will zoom a bit in. So now with the iPad I can do this in a presentation. Okay, so what we see is that, so the yellow dotted line again is the exact solution of the solitone, the red line is the resonance method, and we see that it approximates quite well the structure, so it's a bit off, but okay. And then we see that the exponential integrator method, if we zoom in, it's quite off of the solitone solution, and in particular, numerical instability starts to cook up. And this we see when we go further in time, we see that the numerical solution of the exponential integrator simply blows up, whereas our resonance approximation stays quite nicely close to the structure of the solitone solution. Okay, and so this of course made us very curious whether we can also extend this idea of embedding these nonlinear frequency interactions to a more general setting. So the question is now, if we have a general structure of dispersive PDEs where we have a general differential operator IL, which triggers the oscillations in space and in time, and then we have a nonlinearity F. And the question is whether we can extend this idea from the Kdv equation also to this general setting. And again, so the problem, if you would use classical methods, again, what they would do, they would just decouple the interactions, they would neglect these nonlinear interactions between the differential operator and your nonlinearity because they're built on linearized frequency approximations. And so what I proposed was the following, namely instead of using this linearized frequency approximations, the idea was to really embed the nonlinear frequency interactions into the discretization. And the idea was the following. The idea was to filter out the dominant part in these frequency interactions and solve the dominant part exactly, while only approximating the lower order terms. And this is an interplay between keeping the structure of the PDE, because of course what we would like to do is to resolve as many as possible of these nonlinear oscillations, but at the same time we want to allow for a practical implementation. And here the key question is really, how can we choose this dominant part in an efficient way? And this is where the resonances come into play, because the underlying structure of resonances exactly tell us what is the bad guy or the bad girl in the system. So what we have to resolve exactly and embed in our numerical discretization. And indeed, we could generalize this idea from the Kdv equation to other dispersive equations, such as, for instance, the Schrödinger equation. And here I want to show you a small movie before I talk about the convergence. So in the movie, we see the so-called Typo Effect. So what we do is we solve the cubic Schrödinger equation with periodic boundary conditions in one dimension. And what is very interesting is that if you solve this equation with a step function initial value, then you see at certain time points a quantization effect. And the question is whether your numerical solution will reproduce this in some way. Okay, so now I have to make a new share. Okay, so first let me start with the boring movie. Okay, oops, where is it? Here. Okay, so now what we do is we solve the cubic Schrödinger equation with a smooth initial value. In red, we see this resonance-based approach, so where you really embed the nonlinear frequencies into your discretization. And in blue, you see it's just a classical strength splitting method. And now, boring movie in the sense, okay, the solution propagates in time, and we do not see any difference between the two approximation techniques, and this somehow makes sense. If you take take smooth solutions, and basically you can use any stable method which has a good local approximation property, and you do not really see a big difference between the two solutions. But now let us look at a more interesting case, namely really this Typo effect, this quantization. Okay, so let us now do the same. So we solve the same equation with the same time step size. However, now we take a step function initial value, and what we see is that the solution, okay, we see that at certain time points the solution quantizes. Okay, and this is for certain dispersive equations, this can also be seen on the analytic side. And of course, this is a very nice test example for your numerical scheme, whether your numerical scheme can reproduce this behavior. Okay, and so we go on in the time, and we see that both schemes in the beginning quite nicely reproduce these quantizations. Okay, but then we see at some point that the splitting method, so this is the blue line, starts to oscillate. Okay, and then we see also that the splitting method somehow smooths out the solution, whereas our resonance-based scheme nicely tracks this initial track from the step function initial value. Okay, and then let's just, I mean, it's hard to see if you just let the movie run. Okay, but you see if you stop the movie at certain step points, you really see this quantization effect. And if you go on in time, you see that at some point the splitting approximation is not reliable at all. You get a lot of oscillations in the solution, whereas our numerical scheme quite nicely still preserves the structure of the solution. Okay, so of course also our numerical method starts to oscillate at some point, but I think in all of these long time simulations at some point your numerical solution will receive some oscillations. Okay, so let us go back to the presentation. Okay, and so for the Schrödinger equation, we could also establish a first convergence result. So here you see the scheme, okay, the first order approximation. This is just this resonance-based scheme for the Schrödinger equation. And then let us first look at the convergence plot. So before we saw that these classical methods really suffer from the convergence order at low regularity. And this you see here again, the exponential integrator, it converges very, very slowly. The error of the splitting method, it oscillates widely. And here, of course, you can say you can be lucky and hit a good step size and be close to the exact solution, but you can also be unlucky and hit the bad step size and be very far away. So this, in a sense, is not a reliable approximation, whereas our first order resonance-based method maintains its convergence also under lower regularity. And this we could also show on a theoretical level, namely we could prove global error estimates under lower regularity assumptions than classical methods require. And so now if you do not look too closely at the convergence result, you can say you'll be happy. But let us take a more critical look to the convergence result, namely what can we actually show? So we can show that the global solution, the global error, so the exact solution at time t n minus numerical approximation, can be bounded with order 1. So I have one time step here. If I have the boundedness of one additional derivative in the solution. And this is somehow interesting if you think about the Schrödinger equation and the energy space, because this is exactly where you need H1 solutions. But then the question is, can we deal with solutions in the energy space with this result? And here we have to ask ourselves, what is this R? So here with R, I just mean a standard Sobolev norm. And then you immediately see the problem of this convergence result, namely that you have to choose R larger than D over 2. And this means that you have to work in very smooth Sobolev spaces. Okay. And this is somehow the classical. So with this convergence result, we are back with this classical stability restriction, which you always had somehow if you take naive methods in the global error estimate, because in the end what we have an error recursion. Okay, we are nonlinear, so let's say un plus 1 is just something, and at some point we have a nonlinear term, let's say un square. And then what we want to do is we want to estimate the numerical solution at the next time step by the numerical solution with the time step before. And so if we estimate this, we would like to estimate it by the solution itself. In here, of course, you use Sobolev's embedding theorem, okay? And then we are forced to work in the sufficiently smooth Sobolev spaces. And this is now, of course, very frustrating, and we were stuck a long time at this point because I talked about low regularity integrators. And then who wants to know that, okay, if I measure my error in H100, I only need the solution to be in H100 plus 1. So this is not interesting. What we indeed really want to show is also global convergence results under low regularity. So for instance, in L2. And this is where you turn to the analysis of PDEs, because basically the same problem you face in the local well-posedness analysis of the Schrödinger equation. If you just use naive methods, you also face the problem that you are restricted to smooth Sobolev spaces. And for dispersive equations, this could be overcome with Strichertz estimates. So Strichertz estimates are the essential tool in the well-posedness analysis of dispersive equations in low regularity spaces. So a natural question is, what can we gain from them numerically? And so I will not say too much to Strichertz estimates because there were more experts in the audience. So what basically the Strichertz estimates tell you is that if you solve the linear Schrödinger equation, then you gain in integrability. So if you apply your free Schrödinger group to your function, then you gain something. And now, of course, the question is, can we find a structure preserving discretization such that we also gain something on the discrete level? Okay. And on the discrete level, of course, we do not have this continuous Schrödinger flow, but now our Schrödinger flow is discrete and it lives on these discrete time points n times tau. Okay. And here is where the critical issue comes into play, because these Strichertz estimates, they are not pointwise in time. So here you really have to take the LTP norm and LQX norm. And this is a big, and so for a long question, it was, for a long time, it was an open question in numerical analysis whether a discrete counterpart even exists. And this is a strong contrast to the parabolic smoothing property, because the parabolic smoothing property, of course, is something pointwise in time. So if you take your function v and you transport it with the heat flow, then you know that you gain something in sense of the regularity. Okay. And of course, this parabolic smoothing property, this you can very easily use in numerical analysis, because you just write down your error recursion, and then you know when you sum up, you gain something in the regularity. But this is not the case for the Strichertz estimates. And so one of the first people, as far as I know, who addressed this question of discrete Strichertz estimates were Enrique Suazua and Ignat, and they could prove that these Strichertz estimates do not hold true on a discrete level. But you can show a filtered version. And so together with Frédéric Rousset, we could generalize these filtered Strichertz estimates. And basically what you can show is the following. Namely, you take your discrete Schrödinger flow exponential ITN. And now if you just apply this to your function v, you will not gain, okay, because the Strichertz estimates do not hold true. But what you can do is and where you win is if you take your function v and then you project by cutting off the high frequencies, okay? And you have to do this in such a way that you project on the frequencies lower than capital K, and you have to relate this capital K to your time step discretization, to where your Schrödinger flow lives, okay? So this is the relation. So you have to make a coupling between where you truncate in Fourier space and where your discrete Schrödinger flow lives like. And then for these truncated functions, we can show a similar estimate as for the Schratz estimates for the continuous problem. However, they're a bit weaker, so we lose something on the discrete level. And now the idea is, of course, clear. So what do we do? Okay, so what do we do? Instead, this motivates, so we know that the filtered version holds true, and now the idea is to project our equation. So instead of applying our time discretization to the full Schrödinger equation, in the first step, we project this equation by cutting the high frequencies, and then we apply our time discretization to this projected equation. Because what we win is we can then exploit this discrete Schratz estimates. Okay, and numerically we do not really lose something, because in the end, if we solve the PDE, we have to truncate the frequencies in any way. So this is just basically a spectral method. Okay, and now of course you have two errors. You have the projection error, and you have the time discretization error, and they are related. Okay, you have to relate them in a sense in order to exploit these Schratz estimates, discrete Schratz estimates. And now you can play with these two errors and try to optimize it, and then you indeed get some L2 error estimates. Okay, for H1 solutions. So then you can show that if you take the difference between your exact solution and the numerical discretization of the projected equation with this resonance-based approach, then you get global L2 error estimates for solutions in H1. And here in your convergence order, you lose a little bit. So this delta, so your convergence order depends on the dimension, and you lose a little bit because actually you lose in the discrete Schratz estimates a bit. But you can really establish this L2 error estimates. And now, of course, the next step was, so so if we look at the Schratz estimates more closely, we see that they live on RD, and numerically we cannot really work on RD, so we always have to look at the truncated domain. And so in the next step, what we did is you used similar techniques, so discrete Bourgain space type estimates to also establish this global L2 error estimates under periodic boundary conditions. Okay. And so let me give a short summary. So where we stand so far. So I hope I could somehow highlight give the basic idea behind this new integration technique. Namely, the simple idea was, instead of using these classical techniques of linearizing the frequency interactions, to really embed these nonlinear frequency interactions into your numerical discretization. And what you see in numerical experiments, you see really that this works very well at low regularity, and you can do better than classical methods. And then if you use more sophisticated tools in the error analysis, you can also show this on show global error estimates on the discrete level. Okay, so now this sounds very good, but now let us look at the bottleneck of this approach. So basically what I propose is the following. Instead of discretizing the equation itself, I propose to embed these nonlinear frequencies by basing the numerical discretization on the underlying structure of resonances. And now you already see the bottleneck of this approach, because as in the analysis of nonlinear PDEs, each and every equation is more or less a new challenge. Because here I give a list of 3 fundamental dispersive equations: the Schrödinger equation, the Kdv equation, the Klein-Gordon equation, and on the right-hand side, I give the underlying structure of resonances. And you see from each and every equation, this resonance structure looks very different. And so for each and every equation, we had to design a new numerical scheme, okay? Because we really embed this resonance structure. So we took every equation and had to look at the resonance structure and then write down our numerical scheme. And this is somehow nice if you want to write a lot of papers, but mathematically, this is not satisfactory. So for a long time, an open question for me was, can we find an overarching algorithm? And then a lot of you in the audience will probably also think about the next bottleneck of this approach. Because we exploit so much this resonance structure, the question is, can we also say something about non-periodic boundary conditions? Okay, and so let me now first start with the overarching algorithm. So can we put all this in a more general framework? And then in the very last part of my talk, I will say something about the generalization to non-periodic boundary conditions. And so the overarching algorithm, this is a joint work with Ivan Brunet from the University of Edinburgh. And so what we wanted to do is we wanted to develop a high order framework for a general class of periodic dispersive PDEs. So here we just we look at this general class of dispersive PDEs where the time evolution is driven by a general operator IL, which triggers oscillations in space and in time. And then we have a general nonlinearity. And so what we wanted to do is we wanted to construct an algorithm where you give me the differential operator L and you give me the nonlinearity F. And this algorithm spits out the numerical approximation up to any desired order you want. And now basically you have two problems here. First of all, your algorithm has to embed this general structure of L and F. Okay, so this is not just Kdv or Schrödinger, this is just a general structure. And the second thing is, if you want to have high order approximations, you have to control somehow more and more of these nonlinear frequency interactions. Because if you remember what we did for this first order approximation, we took Duhamel's formula, we iterated it once. Okay, so this is the first line here. And then we tried to embed these nonlinear frequency interactions into our discretization. But now if we want to have higher order approximations, we have to iterate up to the order we want. And in each of these iterations, we have to control more and more of these nonlinear frequency interactions. And so somehow what you have to do is you somehow have to find a framework where you can embed this in a general way. And this is where Ivan had the idea to use the tree series formalism, so to express your solution as a tree series. So basically what you do, you express your solution as a tree series. So each of these terms in your expansion, in your tree series expansion is given by the following. You have your tree, and here you use a decorated tree series where your trees embed these nonlinear frequency, these frequency interactions. So these are the decorations of the trees. You choose the frequencies. So for instance, here you see a tree for the Kdv equation, and here you see a tree for the Schrödinger equation. And so you have your trees, they embed the frequencies, and then you have an integral operator which tells you, which embeds these integrals. So it tells you over which frequencies you have to integrate in each term. Okay, so each of these terms you express as this integral operator acting on the tree, whereas the decoration on the leaves you take the frequencies. And now, of course, so this was an essential idea because this allows you really to encode the general structure of the differential operator and nonlinearity and to control the frequencies up to any order you want. Now, this general formalism allows you to express this and control these frequency interactions. However, numerical analysis, what we have to do is we have to somehow discretize, of course, these integrals. And so this is where you have to define a new integrator, a new operator, namely this discretized integral operator, where basically you apply to each term this discretization technique of the integral in the spirit of resonances. So what do? For each term, you try to filter out the dominant part. This is what this discretization operator does. You embed the dominant part and only approximate the lower ordered parts. And the essential thing is now, if you want to use this expansion and construct really an algorithm, then you have to find the good algebraic structure of this operator. And so we could really find this good structure of the operator, and it allows a Birkhoff type factorization, and this allows you then to recursively calculate each term in your numerical scheme up to the desired order you want. And here I have to say that the Séminaire is very perfectly synchronized because the structure of the operator, of this discretization operator of the integrals, is close to SPD's regularity structures. And next week in the Séminaire, Lorenzo Zambotti will give a talk here about why our department should love regularity structures if we do not already do so. And so, for instance, this is one application where you really use this structure close to the regularity structures in order to bring all these frequencies in a more general setting. Okay. And then, so this didn't only allow us to embed these resonances in a more general setting, but also to treat higher order approximations. And you also see numerical experiments that these higher order resonance-based methods pay off at low regularity. Okay, so now here, of course, you have to be a bit careful, because what does low regularity even mean, high order actually mean at low regularity? Because of course, the higher order we go, also with our resonance method, the more and more regularity we need. However, we see, for instance, for cubic Schrödinger equations with H2 data, we see that really this second order resonance method behaves much nicer than the strength splitting method, where you have an oscillatory error with a high error constant. Okay. And so now in the last minutes, let me and of course, now to be fair, also let me once show a plot for C infinity solutions. So if everything is smooth, we see that we do not gain anything with this resonance approach, but we also do not lose a lot. So the error constants are more or less the same, with more or less the same computational costs. Okay, and so now, so we could put these resonances in a more general setting, but now the central question was still, what about non-periodic boundary conditions? Because the problem with these resonances is that it strongly depends on the Fourier expansion of your solution to really see what these nonlinear frequency interactions are. And what we discovered was, when we looked for a solution how to somehow put these resonances or these low regularity integrators in a more general form to allow also non-periodic boundary conditions, what we discovered was that indeed we can, with this ansatz, also tackle a quite abstract situation. Okay, so we can develop low regularity integrators also for a class of abstract evolution equations. So where basically my time evolution is driven by your operator L, and L does not even have to be a differential operator, and then a nonlinearity F. And so if we want to apply our ideas to this setting, we need basically three main assumptions. We need that our operator L generates a contractive continuous semigroup. So this is to say that we can make sense of the exponential, and in the end that we have stability. Then we have to assume that minus L plus L bar generates a unitary group. So this means that we can go forth and back in time. And then we also have to have a particular structure of the nonlinearity. Namely, we have to be able to separate the oscillations in U and our complex solution U. And for this in this general, and of course the idea would be the same to construct low regularity integrators in this general framework, namely to, instead of using just linearized approximations, to really embed these nonlinear oscillations as far as possible into your numerical discretization. However, in this general framework, it is more difficult because we cannot use Fourier series expansion techniques. With Fourier series expansion techniques, you can directly write down how these nonlinear frequency inductions look like. But here in this general framework, we have to use some more advanced filtering techniques to really see what is the dominant part. Okay, so I do not have, and this is a preprint, which will hopefully be available soon. And so basically, in this situation, under these assumptions, we can develop a new low regularity integrator, which embeds the central oscillations between the operator and the nonlinearity. And so for people who are more in the area of exponential integrators, basically what you see is that you have to impose an additional filter function in your scheme. Okay. And for this low regularity integrator, we can show convergence in a more general setting. So what we can show is that the approximation holds in the space X with first order if my solution lies in the domain of this nonlinear operator. And this nonlinear operator has some kind of commutator structure, and this basically always improves classical approximations if your operator L satisfies this rule. Okay. And this low regularity ansatz in this general abstract framework now allows us to extend the ideas to non-periodic boundary conditions, but also to other equations. So we are not limited to dispersive equations anymore, but for instance to wave type equations, and we can also deal with parabolic problems. Now, of course, the more you can do with your framework, the longer the to-do list also becomes. Because so what I would be interested in is to also go now away from the spectral method. So for the moment, we always somehow use spectral methods as our spatial discretization, which makes sense if you have periodic boundary conditions. But now if you look at non-periodic boundary conditions, the question is, in how far can you couple this, for instance, with finite element methods? And here the main challenge I see, but I'm not an expert in this finite element method, so I think I came here to the right spot. For me, the main challenge at least is to see that in our low regularity integrators, what we always have these phi functions. So for instance, we have to compute something like the phi zero function of TL, which is the exponential of TL. And now if L will be if L is some discretization, spatial discretization, for instance, obtained with finite element methods, then of course the question is, how can I compute this numerically in an efficient way? And again, so for instance, with Krylov subspace methods or layer interpolation, but again, what I don't want to do here is to lose all the regularity again. So this is one of the things I want to work in the next years. And then, so what we did so far for this abstract framework, we could develop first and second order methods. But of course, what sounds very intuitive is to, again, use this tree series formalism to also generalize this to higher order methods. And then What I would be also interested in to look how far we can apply these techniques in the context of stochastic PDEs, because if you think about low regularity problems, normally you also think about stochastic PDEs. And then one central question is also the structure preservation of these schemes. So in particular, if you think about dispersive equations, you have a lot of structure, energy conservation, mass conservation. And a question is, in how far does your numerical discretization inherit the structure and preserve the structure? And in particular, if you then couple it, for instance, with a finite element discretization. And this is all I wanted to say, so I talked a little bit too fast, I'm sorry. But I thank you very much for your attention. And I hope there are a lot of questions, because I have one full slide blank for answers.
Thank you. Merci, Katharina. Donc, est-ce qu'il y a des questions? Je vais lever la main pour ceux qui sont connectés. Est-ce qu'il y a des questions, des interventions? Non, on voit pas.
Alors, je vais peut-être poser une question. Je ne peux pas lever la main puisque je suis l'animateur. Si tu me donnes la parole, Albert.
Bien sûr.
Voilà, donc bon, merci pour ce superbe exposé. Essentiellement, c'est des schémas du premier ordre en temps que tu as. Tes majorations sont toujours majorées par un taux, pas un taux carré.
Oui, but we could also generalize it to second order methods. So second order is also fine, and I think you can also do it up to any order you want in time.
Okay. So the theory is working as well?
Yes.
Okay.
Yes. So you can show something similar as, I don't know, do you see the slide now? Yes,
yeah,
probably.
Yeah.
So you can show something similar also with where you have a more sophisticated structure of your low regularity integrator, but then you can also show second order convergence if basically your solution satisfies a double commutator assumption.
Juste aussi une question. Les simulations sont surtout en dimension 1 d'espace, mais enfin tout marche, tout est développé en
multi, oui.
C'est parce que c'est compliqué à mettre en œuvre en dimension plus grande, ou alors c'est principalement…
No, so we also have, on the towers, we also have 2D experiments,
Ouais.
but the ones I showed are only 1D.
Ça révèle déjà les difficultés, les apports de la méthode. Oui.
But normally this works in all dimensions, so this is…
Benoît, une question.
Benoît. Vas-y, tu peux parler.
Oui, Katharina, je me demandais quand il y a des schémas qui donnent des oscillations très brutales, est-ce qu'il y a moyen de comprendre ces oscillations, d'où elles viennent, quelle est la correction qui est derrière et qui génère ça, ou est-ce que c'est vraiment instable au niveau que c'est simplement la grille que l'on voit?
Je n'ai pas compris.
Quand les mauvais schémas créent des oscillations,
oui.
Est-ce qu'on peut comprendre ces oscillations?
C'est une très intéressante question. Je ne sais pas. Oui, c'est a very interesting question.
Est-ce qu'on peut calculer la correction qui est responsable de ça et éventuellement la corriger après?
Yeah, so this was something, I mean, if you look, okay, oops, sorry, no, this is a bit. If you look at Schrödinger, for instance, this was what I was thinking.
Yes.
If, for instance, you look at the splitting error and it oscillates, and the question was whether you can, for instance, find a filter function which averages these oscillations. So in this sense, but I couldn't do this so far, so I didn't understand. So I just tried to find a different way to do it, but maybe it's possible to really just to find something to correct the splitting method in the sense of averaging at least the error.
Okay.
I tried this for some time, but I didn't see how to do it. But probably I think it's possible, or to really take your scheme and add a correction somewhere which corrects these oscillations.
Yeah. Je crois qu'il y a une question d'Éric Cancès.
Oui, bonjour. Oui, en fait, j'avais une question sur la dépendance par rapport à X. C'est-à-dire que là, tu as présenté des équations homogènes par rapport à la variable d'espace. Qu'est-ce qui se passe si on rajoute un potentiel à l'équation de Schrödinger, par exemple, qui dépend de la variable d'espace? Et est-ce qu'on attend des interactions entre les fréquences du potentiel et les fréquences liées à la non-linéarité?
So you could also do this if you look at the linear Schrödinger equation with the potential. We didn't look at this yet, but some student ones did simulations, and this looked also very promising. To say that if you have a potential under low regularity, to use this method to discretize it in this way. But we didn't do the theory yet. We once had simulations, and this looked nice, but we didn't look further for the moment into this. But of course, this is an interesting question.
Thank you.
Autre question?
Antoine.
Ah, il y a une question à l'intérieur, oui, vas-y.
Oui, c'est un peu dans la suite de la question d'Éric. Donc l'analyse s'est basée sur, en tout cas dans le cas périodique, sur comprendre les interactions au niveau des modes de Fourier pour la partie linéaire. Et quand tu regardes sur Schrödinger linéaire, par exemple, avec un potentiel qui serait quasi périodique, en fait, tu as aussi, tu peux décrire ça comme si c'était en linéaire d'une certaine façon, parce que le problème du quasi périodique, c'est que ça va se faire des résonances au niveau des fréquences.
Ah oui, oui.
Même si l'équation est linéaire. Et bon, alors, dans le cas quasi périodique, c'est pas si c'est compliqué, mais c'est pas. Ça ne changera pas la structure vraiment de. Enfin, si ça peut changer, voilà. Il y a des fois que ça peut faire de la localisation, par exemple, les ondes peuvent rester coincées. Et du coup, ça change complètement la structure de la propagation. Et je me demandais si.
It's very interesting,
ce genre de méthode, en essayant d'écrire un peu plus finement, c'est aussi des Bourgains ont aussi travaillé là-dessus. Et c'est aussi des méthodes de comprendre les choses en Fourier et leur.
Yes, that's very interesting. Yeah, I didn't think about this, but it's interesting.
D'autres questions dans la salle ou à distance? Non, eh bien, on remercie à nouveau Katharina et on va passer à notre café virtuel.